Welcome back to ClearSpot. Building an agentic orchestration system isn't like buying an off-the-shelf monitoring tool. It's designing an intelligent infrastructure that sits on top of everything you already have. Your SCADA system, your inverters, your sensors, and adds a layer of autonomous decision-making on top. And here's the key. It has to integrate seamlessly. It can't break your existing operations. It can't require you to rip and replace everything. In this video, we're going to walk through what modern agentic orchestration architecture actually looks like. The layers, the data flows, how it talks to your systems, how it makes decisions, and critically, how it scales from one site to 50 sites, managing hundreds of thousands of data points per minute. This is the technical foundation that separates advanced systems from basic automation. Let's dive in. Modern agentic orchestration sits on 4 distinct layers. Each layer does something specific. Together, they create an intelligent system. Layer 1, foundation layer. This is everything you already have. Your SCADA systems, your inverters, whether they're SMA, Enphase, Fronius, Growatt, or Solis. Your sensors, irradiance, temperature, wind speed, humidity. Your combiner boxes, trackers, battery systems. This layer doesn't change. Agentic orchestration doesn't replace your foundation. It works with it. Layer 2, the integration layer. This is where, honestly, the magic starts. The integration layer speaks the language of all your equipment. For example, an SMA inverter speaks SunSpec, Enphase uses Enlighten API, and Fronius has the Fronius Solar API. Your third-party monitoring system, well, it has its own connectors too. The integration layer standardizes all of this, translating different protocols into a common data format. It fetches data from your SCADA, from your inverters, from your weather station, and even from your grid interconnection point. And it does all of this in real time. Think of it, really, like a universal translator. Everything speaks different languages, but the integration layer makes them all speak the same language internally. Layer 3, the decision layer. This is where autonomous decision-making lives. The integration layer gives you raw data. For example, inverter A is producing 95 kilowatts. Module string C temperature is 68 degrees. Wind speed is 12 kilometers per hour. Cloud cover is 40%. The decision layer takes that data and, well, it applies intelligence to it. So, this system actually has multiple autonomous agents, each one specialized for a specific domain. The performance agent might ask, given current conditions, what is the optimal operating point? Should we adjust inverter settings? The maintenance agent, on the other hand, would consider, given historical degradation patterns and current sensor data, what's the probability of component failure in the next 30 days? The safety agent checks in, asking, are we operating within safe electrical parameters? Is there any arc flash risk? Ground fault risk? Then there's the compliance agent who wants to know, are we meeting grid code requirements? Frequency response? Voltage support? And let's not forget the optimization agent, who asks, given energy prices, battery state of charge, and forecast demand, what's the optimal dispatch strategy? These agents, they don't run one after another. Instead, they all run in parallel, in real time. Each agent analyzes incoming data from the integration layer, and each evaluates what action would be optimal given its own domain. Then, they coordinate together. For example, the maintenance agent might say, there's a bearing showing early degradation. I recommend increasing service interval by 2 weeks. The performance agent responds, understood. I'll reduce load on that component by 5% to extend its life while maintaining overall output. All of these decisions, they happen in milliseconds. Now, let's talk about layer 4, the execution layer. Once decisions are made, they need to be executed, right? The execution layer triggers actions, like update inverter set point to 97% capacity, notify technician of scheduled maintenance, adjust tracking angle 2 degrees west, log decision and reasoning for audit trail. The execution layer sends these commands back through your integration layer all the way to your physical equipment. So, what we've just described is, basically, A closed-loop autonomous system with hierarchical decision-making. Data flows up, intelligence is applied, decisions flow down, actions occur, outcomes are measured, and, finally, models are updated. This loop, well, it repeats constantly. Multiple times per second for real-time systems and multiple times per day for those longer horizon decisions. The key architectural principle here is separation of concerns. Each layer has a specific job, and each layer is decoupled from the others. That decoupling, honestly, is what allows the system to scale and be maintained. You know, you can upgrade your inverters without rebuilding the decision layer. You can add a new monitoring parameter without retraining all the agents. The system is modular. If the four-layer architecture is the skeleton, the data pipeline is the circulatory system. Here's how data flows in an agentic orchestration system. Data collection. Equipment sends data constantly. Inverters report output every 5 to 15 seconds. Temperature sensors every 30 seconds. Weather APIs every 15 minutes. Grid interconnection data every minute. Some data is structured, like inverter output at 95.3 kilowatts. Some is unstructured, for example, satellite imagery showing dust accumulation. Some is real-time, like current generation, and some is historical, such as 30-year weather patterns. The system needs to handle all of it. Data ingestion. Data arrives through different protocols. MQTT from your SCADA, REST APIs from your cloud monitoring, Modbus from your sensors, direct database connections from your ERP. An advanced system has adapters for each protocol. These adapters normalize the data. They add timestamps, they validate ranges, they flag anomalies. Data enrichment. You know, raw data alone isn't enough. It gets enriched with context. For instance, inverter A is producing 95 kilowatts. That's just data. But when you say, inverter A is producing 95 kilowatts, which is 87% of nameplate, expected for current irradiance levels, 50% below yesterday's due to cloud cover matching the forecast, meaning no anomaly. Well, that's enriched data. It has context, and models can learn from it. Enrichment involves adding weather context, like what was the irradiance at the time. Historical context. How does this compare to similar times in the past? Operational context. What maintenance was happening at that moment? And external context, such as what was the grid price and demand forecast? Now, let's talk about data storage and retrieval. This is where architecture decisions really matter. Real-time data, like current inverter output, needs sub-second retrieval. For that, you need a time series database optimized for fast writes and reads. Historical data, which involves analysis of patterns over years, needs to be queryable. A data warehouse is what you need there. Intermediate data, the features used by machine learning models, requires specific formatting, and you might use a feature store for that. An advanced system doesn't just throw everything into one database. It uses the right database for the right job. Moving on to data access control, this is a critical aspect. Access control is key. The performance agent should see real-time inverter data, but it shouldn't see proprietary pricing information. The optimization agent should see energy prices and demand forecasts, but not raw module-level diagnostics. Different agents have different data permissions. This approach improves security and prevents unnecessary data exposure. Scalability pattern. How does this handle scaling from one site to 50 sites, managing 500 megawatts? Well, the key is separation of real-time and batch processing. The real-time layer covers inverter outputs, current performance, and live alerts. This part runs at each site or, in a high-performance regional hub. The batch layer, on the other hand, handles historical analysis, long-term degradation modeling, and portfolio-level optimization. This runs on cloud infrastructure, usually processing data overnight or during off-peak hours. This architecture means there's no single point of failure, since each site can operate independently. You get low latency for critical decisions because real-time happens close to the source. It's also cost-efficient, as batch processing can use cheaper compute resources. And of course, scalability. Adding a new site doesn't overload the system. An advanced orchestration system will have this separation baked in. But a basic system will try to do everything centrally, which, honestly, creates bottlenecks at scale. Here's where agentic orchestration gets sophisticated. How multiple autonomous agents coordinate without human oversight. Agent communication is key. Agents don't run in isolation. They share information. For example, when the maintenance agent predicts a bearing failure in 20 days, that information needs to reach the performance agent. Why? So the performance agent can reduce load on that component, extending its life while still maintaining output. So, how does this communication actually happen? In advanced systems, it uses a message bus. Agents publish messages about their decisions, and other agents subscribe to relevant messages. Performance agent publishes, setting new, optimal operating point, 96% capacity. Safety agent subscribes to this and responds, checking. 96% is within safe operating envelope, approved. Maintenance agent also subscribes and notes, recording load adjustment for bearing degradation mitigation. All of this, by the way, happens asynchronously. An agent doesn't wait for other agents to approve its decision. Instead, it publishes its decision, other agents react to it, and if there's a conflict, an arbitrator agent resolves it. So what if two agents recommend conflicting actions? For example, performance agent says, increase output to 100% to capture peak generation. But safety agent says, no, thermal model predicts inverter will exceed safe temperature at 100%. Keep it at 92%. This isn't a problem for an advanced system. It has conflict resolution logic built in. The arbitrator evaluates which constraint is more critical. Safety is always prioritized over performance. Then, what's the best compromise? For instance, 97% capacity with active thermal management. And what's the financial impact? Well, 98% output versus safe operations means a slight efficiency loss, but you get equipment protection. So, the decision here is 97% capacity with enhanced cooling. This logic can be rule-based, like safety always wins, or probabilistic, such as weight safety at 90%, performance at 10%. Advanced systems are probabilistic, which allows for more nuanced trade-offs. Learning and adaptation. Here's where it gets really interesting. The system actually learns from outcomes. So, today, the arbitrator compromised at 97% capacity. Then tomorrow, the thermal model sees at 97% capacity with that ambient temperature and wind speed, the actual temperature was 5 degrees cooler than predicted. The thermal model updates itself, its next prediction becomes more accurate. Fast forward 3 months after thousands of hours of operation, and the thermal model is now significantly more accurate. The system can confidently run at higher capacities without overheating. This is continuous improvement, and it happens without any human intervention. The agents, well, they literally get smarter just by operating. Hierarchical decision-making. Not all decisions happen at the same level. Real-time decisions, which take less than a second, might be something like, should we reduce output right now due to a grid frequency drop? These are made by local agents using immediate data. Then, there are tactical decisions, which take seconds to minutes, like, should we initiate a maintenance service call? These involve more data, more analysis, and some coordination between agents. And finally, strategic decisions, which happen over hours to days. Think, should we allocate more maintenance budget to this site versus that site? These are portfolio-level choices, involving historical analysis and predictions. An advanced orchestration system has agents at all 3 levels. Real-time agents feed information to tactical agents, which in turn feed information to strategic agents. The beauty is, each level has autonomy. The real-time agent doesn't wait for the strategic agent's approval to respond to a grid event. But the strategic agent can, learn from patterns the real-time agent is seeing. Integration with your systems. Now, here's the practical question. How does this fit into what you already have? Your SCADA system continues to collect data. Your inverters continue their normal operation. Your monitoring system continues logging. The agentic orchestration layer just sits alongside. It reads your data. It makes decisions. When needed, it sends commands. But, and this is critical, you retain full override capability. If an agent makes a decision you disagree with, you can override it immediately with manual intervention. Or you can update the agent's parameters for future decisions. You can even disable a specific agent if it's, misbehaving. And you can audit the reasoning behind any decision. This is not a set it and forget it system. It's an intelligent assistant that improves your operations while you remain in control. When you're evaluating an agentic orchestration system, here are the architectural decisions that matter. On-premise versus cloud versus hybrid. On-premise means all computation happens on servers at your site or your data center. The advantages? Maximum data security, low latency for real-time decisions, and it works offline. But the disadvantages are a higher operational burden, and scaling requires hardware investment. Cloud means all computation happens in cloud infrastructure. The advantages include easy scaling, automatic updates, and less operational burden. The disadvantages? Potential latency for real-time decisions, data privacy concerns, and ongoing subscription costs. Hybrid means real-time decisions happen on site, while strategic analysis happens in the cloud. It's the best of both, but, complexity increases. What really matters is that an advanced system should support all three. You should choose based on your requirements, not the system's constraints. Data residency and security. So, where does your data live? For solar operators in Europe, GDPR really matters. For operators in the United States, different regulations apply. Some industries even have specific data residency requirements. An advanced system actually lets you choose where your data is stored and processed. It's definitely not a one-size-fits-all approach. Integration depth. Here's where systems really start to diverge. With shallow integration, the system just reads your SCADA, but doesn't send any commands. It's advisory only. That means lower risk, but also less optimization. On the other hand, deep integration is when the system sends commands directly to your inverters, updates SCADA, and controls your hardware. You get maximum optimization, but it does require more rigorous validation and safety measures. Advanced systems actually have staged integration. You start shallow, in advisory mode, and then gradually deepen as you build confidence. Eventually, if you want, you can go all the way to full automation. You're not locked in. You can choose your integration depth. Validation and safety. Before any agentic system sends a command, it really needs validation. Is the command within safe operating parameters? Is it consistent with grid code? Will it cause equipment damage? Advanced systems have multiple validation layers. There's agent-level validation. Did the agent check its own constraints? Then, cross-agent validation. Did other agents flag any conflicts? Next, system-level validation. Does the command fit within site-wide parameters? And finally, hardware-level validation. Will the inverter actually accept this command? Only after all 4 validations pass does the command execute. This is what separates safe agentic systems from unsafe ones. Observability and auditability. You need to understand why the system made each decision. Why did you reduce output? Because the thermal model predicted 110 degrees at current weather conditions, and the safe limit is 105 degrees. How confident are you in that prediction? 92% confident, based on training on 8 months of operational data. What's the expected revenue impact? Reducing output by 5% costs approximately $200 in this hour, but prevents $5,000 in equipment damage. An advanced system has full observability. Every decision is logged with reasoning, confidence levels, and expected outcomes. This is not just for understanding. It's for continuous improvement. You look at the audit trail, see where the system made suboptimal decisions, and feed that back to improve it. Scalability architecture. How does the system handle going from 1 site to 100 sites? The naive approach is to just add more servers. That gets more expensive and, honestly, more complex. The advanced approach? Real-time agents stay distributed, with 1 per site, while shared agents handle portfolio-level decisions in the cloud. Data aggregates asynchronously, not in real time. The system scales sublinearly, so doubling sites doesn't double costs. This is what separates systems that can scale from systems that hit a wall at 10 or 20 sites. Here's what becomes possible with a sophisticated agentic orchestration architecture: portfolio-level optimization. Say you have 15 sites across 3 regions. The weather forecast shows a dust storm in Region A and clear skies in Region B. Advanced systems don't just handle each site independently, they optimize across the portfolio. Move maintenance crew from Region B to Region A before the storm. Schedule preventive cleaning. Prepare Region B for peak generation capture. Coordinate battery charging across sites to handle peak demand pricing. All while maintaining grid compliance at the portfolio level. And honestly, this optimization happens automatically, without human intervention. Predictive maintenance at scale isn't just about saying, well, the bearing is failing. Instead, it's more like, based on 47 similar bearings on your fleet, this one will fail in 18 days. And here's the optimal replacement schedule that minimizes downtime while managing your budget. By combining data across all sites, we can find patterns and predict failures before they cascade. Dynamic pricing response is, honestly, a game changer. Energy prices fluctuate, and advanced systems now respond in real time. So, when prices are high, you maximize generation if possible and hold off on battery discharge. But when prices are low, you optimize for equipment lifetime instead of just output. The system adapts your operation to electricity market conditions, all without the need for human traders. Grid services. Advanced systems coordinate with grid operators. We're talking frequency support, voltage stability, reactive power. The system responds to grid needs in real time while maintaining your revenue targets. These are emerging markets, folks. Advanced orchestration systems are the only way to capture them at scale. So, what's critical here is that all of these capabilities are built on the foundational architecture we discussed earlier. They're not just add-ons. Nope, they're natural extensions of a sophisticated orchestration design. Alright, when you're evaluating agentic orchestration systems, here's what to look for. First up, architecture maturity. Can they explain their architecture clearly? Do they have separation of concerns between layers? Do they support both real-time and batch processing? Next, integration flexibility. Do they integrate with your specific inverters, SCADA, and sensors? Or is there a long custom integration phase? Then, safety and validation. What validation layers do they have? How do they prevent unsafe commands? Can you audit decision reasoning? Scalability design is also key. How many sites have they deployed at? What's their maximum scale? How does performance degrade as you add sites? Learning and adaptation. Do their agents improve over time? How do they measure that improvement? Can you see the before and after accuracy? Observability is crucial. Full audit trails? Explainable decisions? Or black box decisions you can't understand? Systems that are transparent about their architecture and limitations are more trustworthy than systems that hide complexity. Advanced systems invite scrutiny. Basic systems hide it. What we've covered today is the architecture that underpins modern agentic orchestration. We've got 4 layers: foundation, integration, decision, execution. Data flowing up, decisions flowing down, learning happening continuously. Multiple autonomous agents making specialized decisions, coordination between agents, conflict resolution, hierarchical decision-making from real-time to strategic. This is how advanced systems work. The key takeaway here is that a sophisticated agentic orchestration system isn't a replacement for what you have. It's a complement. It sits on top of your existing SCADA, inverters, and monitoring, and adds intelligence on top. It integrates with your systems. It respects your data and safety requirements. It improves continuously. It remains under your control. If you're evaluating orchestration systems for your portfolio, look for architectural sophistication. Look for transparency. Look for evidence of real-world deployment at scale. The systems that are serious about this have published their architecture. They can explain how they handle edge cases. They have production deployments managing real revenue. Like, share, and subscribe for more solar insights. ClearSpot. Smart device. Smarter decisions.